Okay, hi everyone. Again, here we are. We are now at the third process. It is isothermal. Okay, isothermal process. Okay, in this isothermal process, we know that the temperature is constant. Okay, the first thing that we are going to derive here, it is the relation PVT. Relation PVT, okay, at temperature constant. What will be the relation PVT at constant temperature? Okay, now we will just write, we will do the same. Okay, PV equal to mRT. We will consider for two states. Okay, two states. Two states. State 1, P1 V1 is equal to mRT1. State 2, it is P2 V2 equal to mRT2. Nice. Here the temperature is constant. T1 is equal to T2 and this is constant. Okay, we will derive what is the PVT relation between them. So just find out what is T1 here and T2 here. It's okay. What is T1? T1 will be P1 V1 upon mR. And T2 the same way. P2 V2 upon mR. Okay, then we will just equalize. T1 is equal to T2. What does it mean? It means that P1 V1 upon mR is equal to P2 V2 upon mR. This is the same substance, so mR will be cancelled out. So it means that we have P1 V1 is equal to P2 and V2. Nice. Now it is derived. Let's go for the next step. This is now we are going to calculate what is the volume. Okay. What is the volume? Okay. Not the volume, but the work done at constant temperature. So if temperature is constant, what will be the work done? Okay. We know that the work done V2 is in V2 V1. So let me just draw first this one, V and P. This is P and V. Okay, P and V. So the work done in this one. So see how will vary or how will be this change. Okay, this one, this how can I say, the line in between PV when temperature is constant will be a kind of line like this. Suppose here P V is equal to mRT. We know that M and R are constant. Okay, are constant. Now temperature here also is constant. So it will be what? PV equal to C. So it means if I just draw the graphic of P, the graphic of P will be 1 upon V time constant. You see this graphic? So this graphic here, 1 upon V, it is the same as we were just, you remember a little bit of math. When we have y equal to 1 upon x, how is this graphic drawing? It is like this one. This is like x, this is y, and this is x. So the graphic is something like this. Okay, and this will be the same for this process. It will be something like this. Okay, not a straight line. I will consider this one the first state and this one is the second state. Okay, the second state. Now, this is isothermal process. Okay, and here temperature is constant. So it means that here I have V1 and here I have V2. Just to see, okay, is it a compression or an expansion? V1 is less than V2, so volume is increasing. It means that this is an expansion. Okay, so work done here is done by the system because it is expanding. When this is expanding, work done is doing by the system, and this is a positive work done. So when there is a compression, work done is also, work done has been done for someone else on the system. So it will compress the volume. Volume will decrease just like this. Okay. See, this one. And now see, this is how can I say this one? This is an isothermal process. So this area here will express our work done. This area here, this area here, between these two atoms. Okay, so it will be P. We have P dV as we know. Okay, change in pressure. So we know, okay, what is P? We know that PV is equal to mRT. Nice? It's okay, no problem. But we derived also the relation between P2, V2. Nice? We derived. What is the relation between PVT for this one? Just see this. Okay, what is the relation between PVT? This is this one. Okay, we know this one. And this can be expressed as we said here, PV equal to C. Okay? PV is equal to C. Okay? What is this C? This C is nothing more or less than, just check here. Mass is constant, R is constant, temperature here is constant. So PVC equal to C. Okay? It's constant. All of them are constant. Even for those, from those old process, you can just consider this one also. So, okay, when volume is constant, everything is constant. That's why for those one also can you consider. See, PV equal to C. Nice. Okay, here we will find what is P. Okay, what is P? So P will be C upon V. Okay, substitute this in this one. So work done will be, okay, the integration from V1 to V2, these two parts, and this guy will be C upon V, and here dV. So C is constant, so I will just integrate from this one, V2 upon V1. So this will be dV upon V. Okay, so work done will be C, and this integration, dV upon V. Just remember, this is math. Okay, whenever I have integration of dx upon x, this is what? This is ln of x. Okay, ln of x. So this will be ln of V in between V1 to V2. Okay, so work done will be C of ln of V2 minus ln of V1. Okay, so what is this? C, we know. What is C? C is equal to PV. Okay, now here we have states, so we can just say C is equal to P1 V1 or C is equal to P2 V2, because they are all the same, because P1 is equal to P1 V1 is equal to V1 V2, so P1 V2. So yeah, you can just substitute this one. This C is P times V. Okay, and it can be given state. For state 1, just write down here 1, 1. Then here, ln of V minus ln of V1, ln of V2 minus ln of V1, it will be what? ln of V2 upon V1. Okay, this is the work done. Now, from here, you can express this in many ways. Because you know that P1 V1 is equal to P2 V2. You can express this V2 upon V1 in what? Because what is V2 upon V1? Just come here and divide it by V1. And V1 and V2. Just come here and divide it all by P1 and P2 and V1. Divide all the expression here by P2 and V1. Here you will get V2 upon V1, and here you will get P1 upon P2. Okay? As they are the same, V2 upon V1 are the same, so I can substitute. Work done can be P1 V1 ln of P2 V2. There is many ways. I will write down all the ways to you to write the work done on isothermal process. So the work done on isothermal process, can be written like this one: P1 V1 ln of V2 and V1. It also can be written as P1 V1 ln of What is V2 upon V1? From here, it is P1 upon P2. So, this will be P1 upon P2. Okay? And this also can be written in this way. This will be, what is P1 V1? P1 V1, we know it is nRT1. Okay? P1 V1. So we can also write down this one as this mRT1 ln of P1 upon P2. Okay? And if you do not want to write P1 upon P2, write. It will be mRT1 ln of V2 upon V1. But the point is that, okay, why too many formulas? These formulas you will use according to the data that they will give to you. Okay? It's not just, okay, I can calculate. No, you will use wisely depending on the data that you have. Suppose I have only volume, okay, I have first volume of the gas, and I have the first pressure and the second and the last pressure. So I will use this one. This formula is suitable to calculate what is the work done. Suppose I have the mass of the gas, and I have R, and I have temperature, and I have P1 and P2. This formula should be the easiest one. Suppose I have temperature and volumes only. So just calculate by this one. So it depends on the point that you are going to use. Okay? Now that we are done with the work done for isothermal process. Okay? Now what's the next? What is delta U? What is internal energy? Okay? What is internal energy? Internal energy. What is internal energy for this work done? Okay, that's the point. It's the internal energy. See, as I told you in the beginning, internal energy do not depend on any characteristic of the gas. It only depends on the temperature of the gas. So it means that internal energy is a function solely of the temperature of the gas. So here, as we are speaking that in the isothermal process, temperature is constant. So here, temperature doesn't change. So as the internal energy is a function of temperature, temperature doesn't change, temperature is constant, so internal energy will be zero because it will be mCV delta T. It will be mCV T1 minus T1 because T2 is equal to T1. Okay? T2 is equal to T1. They are the same. So this will be 0. So internal energy will be 0 directly. Okay? Okay. Now what will be heat transfer? Q, that is heat transfer. Okay? Q heat transfer will be work done plus delta U. Okay? We know this one. So now that we know that delta U is 0, so Q will be all equal to work done. That's why the heat transfer will be all converted. If I supply heat at constant temperature, this heat will be converted into work done directly. So this can be written like this: P1 V1 ln of V2 upon V1. And it has many formulas I have already written there. Okay? So whenever the temperature is constant, the heat transfer is equal to work done because there is no internal energy. Now the last one but not the least, okay, this is 5. This is change in enthalpy. Change in enthalpy. What is change in enthalpy? We know this will be what? Will be P2 V2 minus P1 V1. Okay, this will be change in these guys, and change in also U2 minus U1. Change in enthalpy will be this one. Okay, so here P2 P1 minus P2 P1. We know that P2 V2 is equal to P1 V1. No, we know this, right? So from here we know this. Okay, and also, as P2 is equal to P1 and V2, we know that T1 is equal to T2. So directly we can just write this one is equal to this 0. And internal energy, mCV delta T. Here it will be mCV T2 minus mCV T1. So this is the same substance. So it means that this will be the same mass, the same constant volume, specific volume, and the same temperature minus the same mass, the same constant volume or specific heat at the same volume, at constant volume, and the same temperature. If I subtracted this one, it will be 0. Okay, but anyway, I will write just this one. So this one will be mR T2 minus T1, and this mCV T2 minus T1. Okay, directly you can see T2 is equal to T1. This will be 0 plus 0. So delta H is 0. Okay, this will be 0 directly. Okay, this is 0. So thank you, and hope seeing you in the next video. In the next video we will speak about the second last process, and this will be a diabatic process. Thank you.